but not too closely. 2 weeks ago, we defined simplicial homology, and let us recall that definition very briefly without writing anything on the blackboard. We're given a simplicial space. To each simplicial space, we will eventually assign an abelian group, Hn of X, where X is the given simplicial space. We do that in 2 steps. In the first step, we assign to the simplicial space and to the natural number n an abelian group called the chain group. Its elements are linear combinations with integer coefficients of simplices. Once this is done, we define the boundary operator, which is a linear operator from n-dimensional chains, from the n-dimensional chain group to the n-1 dimensional chain group. This operator has the Poincaré property, which says that the kernel of the operator Dn contains the image of the previous boundary operator Dn plus 1. Once this is done, we immediately define the nth homology group of the simplicial space X by setting it equal to the quotient of the kernel of Dn by the image of Dn plus 1. That is the definition of simplicial homology. This lecture, however, begins not with simplicial homology, but with 2 algebraic lemmas where nothing about simplices is mentioned. Section 1, algebraic lemmas. The first lemma that we will consider is the so-called 5 lemma. Which is due to Sam Eilenberg. Sam Eilenberg was an American mathematician who spent most of his mathematical life in Paris. He was one of the members of the Bourbaki group. He is perhaps the most important creator of algebraic topology. He certainly is the creator of homological algebra, and in a certain sense, the precursor of category theory. So the 5 lemma is the following. We have a diagram of groups shown by black dots and homomorphisms between these groups. The groups are abelian. Diagram has the form that you see. we know that the rows of this diagram are exact. The two rows, both rows, are exact. And we also know that the vertical arrows, this arrow, this arrow, this arrow, and this arrow, are isomorphisms. In that situation, the lemma asserts that this vertical arrow, called phi, is also an isomorphism. So let us prove this lemma. To do that, we must prove two things. That this vertical arrow is surjective and that this vertical arrow is injective. Let us prove surjectivity. This means that for any element A from this group, there must exist an element in this group which is mapped by phi to A. Our argument is a typical diagram chase. We'll be moving around the diagram using its properties to find the required element here. So let us apply this homomorphism to A. We obtain some element B. Now, this arrow is an isomorphism. There is a well-defined element C up here. Now, let us look at what happens to B under this homomorphism. I claim that it goes to what? It goes to 0. Why is that? Well, because the horizontal sequence of groups is exact. This is B belongs to the image. The image coincides with the kernel, so B has to go to 0. Now, under this isomorphisms, 0 goes up here. Since this square is commutative, C goes to 0. Now C goes to 0. It means that it's in the kernel. Since the top row is exact, this means that C also belongs to the image of the previous homomorphism. So there is an element B, D, that goes to C. And since this square is commutative, D is mapped to A, and we have proved surjectivity. Injectivity is proved in a similar manner. Let me begin the proof without writing anything on the board. What do we have to prove? We have to prove that only 0 goes to 0. That's injectivity. Now we assume the converse. Let some non-zero element go to 0. Then we look at what happens to this element, and so on. So we can assume that this lemma has been proved. Now, write it as follows. I will erase the proof here, and instead of phi, I will write isomorphism symbol here. So this is the phi lemma. The next lemma is called short to long lemma. What does it say? Well, it says the following. Suppose we have a short exact sequence of chain complexes. Short means that it consists of 3 terms, 3, 1, 0. So this is exact sequence of chain complexes. In that case, it induces, in a certain way that will be described in the proof, an exact sequence of homology groups. So call this homomorphism I, this one J. So this is here I star, H and C prime. This is J star and H and of C double prime. And so on. Oh yes, and the important thing is that the next homomorphism is to Hn minus 1 of C, the C here. Now these homology groups are not simplicial homology groups. They are homology groups of these 3 chain complexes. These 2 arrows are simply homomorphisms of homology groups induced by I and J. Whereas this homomorphism remains to be defined. We must define this homomorphism, and we will do that presently. Let us write this picture in more detail. Recall that a chain complex what this really means is the following. We have here CK here we have C K prime. Here we have C K double prime. Here we have 0 and 0 here. And here we have ck minus 1 with the operator delta k, dk. So here we'll have dk plus 1. Go down here. We have d prime k here. C prime k minus 1. C double prime k minus 1 with d double prime k here and 0 at the end, and the other deltas working here. So what do we have to do? We want to construct this homomorphism. To do that, we take an arbitrary element of H. So let me use a different. Let us take H and C double prime and take an element of this group, and we want to assign to it an element of this group. So this element has the form C double prime. Oh, sorry, this is not N but K. C double prime K, where C is a cycle. D double prime K of CK is 0. And we want to assign it to it an element CK minus 1 of the homology group H and HK minus 1 of C. So the first thing that we do, we'll look at this diagram. This fellow CK double star lives here. We're going to do some diagram chasing with it. First of all, this goes to 0. Therefore, there is an element C prime K here that goes to this element. We take its image down here. We get an element C prime K minus 1. So this, by definition, we take C prime K minus 1 as D prime K of C K prime. Now, this sequence of abelian groups is exact. And so there is a unique C K minus 1, so unique CK minus 1 in CK minus 1, such that CK minus 1 is mapped to CK minus 1 prime. And so by definition, we define D prime, D star of this element of the homology group as C K minus 1 here. It's easy to show that this will be a cycle, and so the corresponding homology class is an element of the homology groups. So we have constructed the D star. What remains to do is to prove, first of all, that D star is well defined. Secondly, we must prove that the sequence, let's denote it by a star like that, the sequence is exact. Both statements follow directly from the construction and the definitions. So I will leave that to you people out there. So much for the two algebraic lemmas. Let us erase all this. And go on to the next item of today's lecture, which will be the exact homology sequence for pairs. This sequence we have already written out 3 weeks ago when we studied cellular homology. It is the same for simplicial homology. When studying cellular homology, we did not prove that such a sequence exists, although I did some hand waving about that. Now we will give a proof of this exact sequence for pairs. So this is section 2. It is called the exact homology sequence for pairs. It has the following form. It begins with H n of A. Then this is taken to H X. And then we have J star that takes this to H n of the pair. And then the next arrow, as you have probably guessed, is called D star. And what you get here is Hn minus 1 of A. And then the sequence continues in a similar way. Let me explain what are these symbols here. We have a pair. A simplicial pair. X A, which means that X is a simplicial space and A is a simplicial subspace of X. What is this group? This group is the nth relative homology group of the pair XA. How is it defined? It was defined 2 weeks ago, but let's recall the definition. It is simply the group consisting, obtained from the chain group of all n chains such that the coefficient at simplices from A is 0. Once again, we consider the chain group CNXA, whose elements are such elements of CNX, which contains CNX elements such that the coefficients at simplices from A are equal to 0. And so the statement that we're now going to prove says that the sequence for any simplicial pair is exact. It turns out that the proof is quite short because we have the needed machinery to make it short. Let us write out the following short exact sequence. Of chain groups. These are now simplicial chain groups. I'm sorry. Simplicial chain complexes. So this is a chain complex of A. Then comes the chain complex of X. And then comes a chain complex of XA. And then we have 0. Now this short exact sequence of chain complexes is obviously, this short sequence of chain complexes is obviously exact, because exactness means here that here we have an isomorph, a monomorphism, and here we have an epimorphism. And this immediately follows from definitions, because what disappears when you come to here to here, it is precisely those chains that have simplices in A. So this is obviously exact. Now we apply the short. Here we have something which we call I star. Well, a second star here. So it's not confused, it's not the same. Like I star and J star, which are defined as follows. Well, I've already explained. Here, it's simply the inclusion. And here, we just look to every chain. From here, we assign 0. We assign the chain here by setting equal to 0 those coefficients that are at simplicities from A. So this is obviously exact. And now, by the short to long lemma, we obtain the sequence you will perhaps remember that this sequence looks exactly like the homotopy sequence for pairs that we studied, I think it was 4 lectures ago. So let's continue our study of properties of simplicial homology. And what we are going to consider next is something called the Meyer-Vietoris sequence, which is a long exact sequence. Which is extremely useful for the computation of homology groups, in particular simplicial homology groups, because it allows to construct simplicial spaces by putting together 2 simplicial spaces with a common subspace, and thus building our simplicial space from larger and larger building blocks. This sort of activity will be carried out at the exercise class. So the Meyer-Vietoris sequence. So this is not ancient mathematical history. This is relatively recent, at least from my point of view. This sequence was not first invented by Meyer or Vietoris. The first person who wrote and used this sequence was M.F. Bockstein, a Soviet mathematician, who incidentally was my thesis referee when I did my PhD. So at least it's something that appeared during the period of my living memory. Though perhaps to you it may seem more like ancient history. Anyway, what does the Mayer-Vietoris sequence say? It says the following. Let x1 and x2 be simplicial subspaces of a simplicial space X. Let Y be the intersection of x1 and x2 and X be the union of x1 and x2. So we have the following picture. We have this big fellow X. It consists of two parts, x1 and x2, whose intersection is Y. And the exact sequence that we will now write out involves all these characters. It has the following form. We begin with Hn of Y, of course, the smallest character here. Then we have a clever map of that into Hn x1 plus, so Hn x2. These are abelian groups. We just take the direct sum of the abelian groups. Then this is mapped to Hn of x, of the big fellow of x, of the whole x. And then we have something whose name you have guessed, and it's D star. And what we get here is Hn minus 1 of Y, and so on. Now, I'm going to define I star, J star here, and D star here. And once this is done, I claim that this sequence is exact. That is what I have to prove. As I'm sure you have guessed, to do that, I'm going to construct a short exact sequence of chain complexes. Namely, this sequence 0 goes to CY goes to CX1 plus CX2. What does this plus here mean? Well, these two fellows are chain complexes, and plus means that we just add the corresponding chain groups at each level n. And from this, we go on to something called C of x, and then the next one will be called, no, there is no next one. This goes to 0. So we're going to construct this short exact sequence of chain complexes, and then apply the short to long exact lemma and obtain this. So as not to confuse things, I'll add another star here and another star here. These are not the same symbols, although they have the same origin, so to speak. Okay, so how do we do that? Well, we need some notation. Let us denote by I1 the embedding of x1 in x, and by I2 the embedding of x2 in x. And now I will construct this map I star as follows. For any oh, I'm sorry. I got this all wrong. This is y, sorry, y in x1. And this is y in x2, sorry. And so it have an element C from here to it. I will assign y I star the following element. It will be I1 star of C minus I2 star of C. Okay. And then I will write denote by J1 the inclusion of x1 into x, by J2 the inclusion of the inclusion of x2 into x, and for an element C1, C2 from the sum here. To this such an element, I will assign the element J1 of C1 plus J2 of C2. And I made another mistake here. This should be really this. And there should be a minus sign here. Now, first let me explain the minus sign. Well, it has to do with the following. If we have a simplex in x2 and a simplex in x1, then these are oriented simplices. And they acquire, they give orientations to this simplex. And they have to be, and these orientations are opposite here. So we have to have a minus sign so these things cancel out. Now, all that remains to be done is to apply now exactness of the sequence. Let's denote it by star. Follows from the short to long exact lemma. Of course, I did not explain in detail why this sequence of chain complexes is exact, but that's obvious. It follows immediately from the definitions. So we have obtained the Meyer-Vittoris sequence, which I hope you'll enjoy applying to solve various problems. The rest of this lecture will be devoted to proving the most important property of simplicial homology, namely that simplicial homology is homotopy invariant. That is a difficult theorem, and I will not be able to complete the proof today. It will be, I will stop at 11. And the rest of the proof will be presented to you next time. Our first step in the proof of homotopy invariance is something which is called chain homotopy. Well, chain homotopy is, so to speak, the algebraic clone of a homotopy of simplicial spaces. The definition is rather unusual. I'm sure it was not easy to think up this definition. Here it is. Supposing we have two chain maps. We at this moment are in algebra. We're talking about algebra. We have two chain maps, Fk and Gk. They're maps of chain complexes, of chain groups. Ck to Ck prime to Ck double prime. And these two maps are called chain homotopic. Chain homotopic. If we have the following situation, I'll draw a complicated diagram. Well, not very complicated. Here we have C, K prime, K plus 1. Then we have C prime K. Then we have C prime K minus 1, and so on. Here we have C double prime K plus 1, and we have two maps, or two homomorphisms to be more precise, Fk and Gk, going down here, and similar K plus 1, K plus 1. Similarly, down here, we have C double prime K with Gk, Fk here. I won't write the names of these guys. C double prime K minus 1, and so on. And so on in this direction as well. So these two maps of chain complexes are called chain homotopic if there exists a sequence of homomorphisms dk of C prime K to C double prime K plus 1, and such that we have the following equation. If we first, well, I'll draw them on the diagram and write the corresponding equation. So here is the K, this is the K minus 1. Here we have the K plus 1. So these two maps, or these two homomorphisms, two morphisms of chain complexes are called chain homotopic if we have a sequence of homomorphisms that group homomorphisms decay such that we have the following equation. If we first do decay and then do the k plus 1 double star, and then to that we add the k minus 1 and then first we do the wait a minute. No, it's not a double prime, it's just one prime. The k minus 1 d prime k. And this must equal to the difference between gk and fk. Let's look at this equation on the diagram. So we start here. We have an element here. Now we do decay, we come here. Then after that, we do this boundary operator. So I was right the first time. This is d k plus 1 double star. So we come here. On the other hand, we're starting from here. We can first go here by means of dk prime, and then apply dk minus 1. We come here. And what we must get is the difference between these two characters. Let me draw a kind of diagram. So we have this, this, and this. And what we do, we go like this, and like this, we go like this, and then like this. And what we get here, is the difference. So this is not a commutative. This diagram is not commutative. What we get here is the difference between these two maps. Now, about chain homology, I will state the one. This is the chain homology lemma. It says that if, so suppose that fk and gk are chain homotopic. Then the lemma asserts that the family of induced homomorphisms coincide. Okay, so I'm going to prove this. So let us take, what do these fellows do? They take the kth homology group of C prime to the kth homology group of C double prime. Let us take an arbitrary element of the group H K C prime. So an arbitrary element has the form ZK, where ZK lives, well, let's call it ZK prime because it lives in CK prime, and it's a cycle. It is a cycle, so it's the differential, its boundary operator of ZK prime is 0. So what we want to do is to assign to this an element of H K C double prime. Well, what do? We're going to rewrite this equation for the Z prime. So we have D double prime K plus 1 D K applied to Z K prime plus D K minus 1 D prime K applied to the same Z prime K. And this must equal the K Z K prime minus Fk of Z K. Now, let's look at this term here. What does it equal to? Well, if we take away these parentheses, we have D prime K of Z K prime, which is 0 because it was a cycle. So this cancels out. And we are left with this equality. What does the equality say? Let's rewrite this term as follows. It's D prime K plus 1 applied to dk of Z prime K prime. So what is this telling us? Well, this last equality is telling us that these two cycles differ by a boundary. So these two cycles differ by a boundary. Well, that means they are homologous. And this means that these two homomorphisms of homology groups must be exactly the same. So that's the end of the story about chain commodity. We will use this fact eventually. And perhaps going ahead, let me explain how it's going to work. Well, we know that we have proved, if we have constructed a chain homotopy for simplicial complexes, then we are able to prove that the two induced homomorphism of homology groups coincide. And now, from this, it is easy by a standard argument to prove that the homotopy of that the homology group of a simplicial complex is the homology group of a simplicial complex is homotopy invariant. Okay. Next item that we will study today is something called augmentation, which I should have explained a long time ago when we were doing cellular homology, but I ran out of time and didn't explain it. So here's the explanation now. Augmentation. Now let's look at at the very end of a chain complex of a given simplicial space X. It has a following form. We have proved previously that if X is path connected or disconnected, and then H0 of X is the group of integers. The converse is also true, at least for finite simplicial spaces. Now, we don't like this situation And we're going to change this chain complex to a different one. It begins in the same way, X. Then we go to D1, we'll do D1, that, just to see 0 of X. But then instead of going directly to 0, we will take this to Z, and then take Z to 0, and obtain a new chain complex. How is this map here defined? Very simply, an element here is the sum of some integers vi multiplied by some zero-dimensional simplexes, a linear combination of zero-dimensional simplexes. Now there's only a finite number of integer coefficients which are not zero here. And so we map this to the number sum of Z A. So this is the definition of the augmented chain complex. And the corresponding groups H0 of this complex will be denoted H0 X tilde. From the definition, it immediately follows that this group is 0 if and only if X is connected. So actually, we should have defined the chain complex of a simplicial space from the very outset as this chain complex rather than that one. And then we would have a much nicer formulation for this theorem. This fact follows immediately from this fact and the definition here. And I will need one more term. Supposing we have a simplicial map of a simplicial space X to a simplicial space Y. So no, let's say this on the chain level. Supposing we have a map of a chain C0. I'm in pure algebra at this point. So I don't care about the fact that there are chains of a simplicial group. That's just the general algebraic definition. So such a homomorphism is called augmentation preserving. Preserving if we have the following. F tilde of any chain zi is sigma 0I. Will be equal, must be equal to the sum of zero-dimensional simplices here. With other coefficients, j, with the following equality: the sum of the zi's must be equal to the sum of the zij's prime. I'm sure you have understood why we need this definition, because when we have two chain complexes, say of simplicial chains, and we have one map to the other, and we want to work with augmented homology, and then we must have this condition in order to obtain an induced map of homology groups. So we will very soon need the notion of an augmentation preserving homomorphism. And I was about to go on to the next step in our proof of our of the homotopy invariance of simplicial homology. But I won't get very far there. I would just have enough time to introduce one term in terminology. So this will be paragraph 6, and it's called the cyclic supports. So I'll have time just for one preliminary definition. Let A be a simplicial subset of a simplicial space X. Then A is called a cyclic if for all n h n of A is 0. Here h n tilde denotes augmented homology, which for n greater than 0 coincides with the ordinary homology, but for n equals 0 is slightly different from it. And we simply require that the homology of this set A is trivial. The next step will be to define a very clever and unexpected notion, which is called um, a cyclic support theory. We will define the notion of an acyclic support of a simplex and prove an acyclic support lemma. This lemma will be eventually used to prove the existence of these homotopy chain operators that we studied 15 minutes ago. So that is all for today. The next lecture will be at the same time in exactly a week, and we will be finishing the proof of the homotopy invariance of simplicial homology, and we'll also prove a beautiful theorem known as the Hurevich